Hello learners, welcome to my channel RG Global Academy. In this lecture, you are going to learn about Hamming error correction codes. I will start with the terminology of this field like parity check, Hamming distance, and then I will walk you through the steps of encoding and decoding that are required for 7.4 Hamming single error correction code and then 12.8 Hamming single error correction code. Let's start. Hamming code was invented by Dr. Richard Hamming in 1950 when he was working in Bell Labs. He faced the problem that data is getting corrupted and there was no way of correcting it before him. There was ways to detect it, but no correction was still there. So he invented this Hamming code which can detect and correct both. Dr. Richard Hamming was an American mathematician, and his contribution is immense in computer engineering and telecommunication. He developed L2 programming language that was very prevalent during his time. Later on, Fortran language was developed. He also developed this 7.4 Hamming code, which we are going to learn in detail, and the terminology like Hamming distance, which tells what is the capability of a code word, how many error it can detect and how many error it can correct, etc. So for his contribution, he was also given Turing Award, ACM Award, among many others. So let me tell you first what is the requirement, why it is so important that error is detected and corrected. So in this picture, you are seeing two people, Alice and Bob. They are communicating over the computer network. We call it a transmission line, and they are sending a sequence of zeros and ones because message or information or data which is a string of binary bits. One represent high voltage and zero represent a low voltage. So there may be chance that one of the bits get flipped, high voltage becomes low voltage or low becomes high. So during this condition the entire bit string is wrong. So it is very important that this error is detected and corrected also. Not only unintentional corruption of data, sometimes intentional corruption of data also happens. As seen here, Mallory is the guy who is intruding their communication between Alice and Bob. Maybe he is the one who is changing these bits. So for any reason, intentional or unintentional, if data is corrupted, that needs to be detected and corrected. That's why this field is so important. And fortunately, Richard Hamming invented a code which can detect and correct errors, and we are going to learn about it now. Data can be corrupted during transmission, but not only during transmission, it can be corrupted when data is stored in memory inside the same computer. So the solution is to detect the error and correct it so that you get the right result. And before going through that procedure, let's see some definition about types of error. Uh, the data can be corrupt in a single bit position, which is called single bit error, where it is shown that sender is sending these 8 bits of data and receiver is receiving, but in 1 bit position the 0 flipped to 1, and that is what is called single bit error. This bit flip can happen in multiple bit position also, like it is shown here. Here this 1 became 0, sender sent 0, it became 1 here, 1 here, and there are 4 bits that got flipped, but the span of this error is 8. So it is called burst error, and the burst length is 8. Single bit error is more frequent than burst error, and we are going to see Hamming code which can correct single bit error. To detect and to correct errors, sender sends extra or redundant bits along with data bits, and this mechanism is called encoding. Sender side has one encoder It will take the message or useful information bits, which is called the data. It will feed it to a generator, and the generator will decide how many extra redundant bits are required and where should be their values. And it is generating data and redundant bits together. These redundant bits are also called check bits. So data and check bits together, it is called code word, and this encoder is generating the code word at the sender side, and then the code word is sent through the noisy transmission line, and after receiving the code word, receiver will send it to a checker to check whether the code word that he has received is right or wrong. If right, then it will extract the data, and if wrong, if the checker has the capability, or basically if the code word has the capability to correct itself, then the checker will correct it and send the right data. So as I said, 7/4 Hamming code can detect and correct single error, and even we are going to see a bigger example of 12/8 single error correction code. So at the receiver side itself, the code will be corrected. If the correction capability will not be there, then the receiver had to request the sender to retransmit the data. But at the receiver side, if this correction capability is there, then it is much more efficient, because again you are retransmitting the same message with noisy transmission line, so that efficiency is not that much. So correction capability at the receiver side makes the communication much more efficient. Here I will show you some example of data words and code words. In a block of data, this block of data is divided into data words, each k bits long. So with k bits, there can be 2 to the power k data words, and r extra bits are added with k bits. So the length of the code word will be k plus r, which we can call it as n bits. So with n bits, there can be 2 to the power n code words, but not all code words are used. Only 2 to the power k code words are valid and others are not used. Why? Because if the code words are very close to each other, then it is very difficult to correct the code. Like here I am showing a table of data word and code word. Data word is 4 bits long. So with 4 bits, there can be 2 to the power 4, 16 valid data words are there. And now you can see with every 4 bits, 3 redundant bits are added. And now the whole thing together is called a code word. And the way the code words are assigned, 000 here, then the next one 011, that technique we are going to see. But you can see that if the code words are uh, vary from each other, maximum distance is there, then it is better for the detection and correction capability. So how I will tell you the mechanism by which the distance between code words are found. So each code word is a string of zeros and ones. Depending on number of ones in a code word, it is called the weight of the code word. So if you take example of these two code word, so this code word has 1, 2, 3 ones, and the next one has also 3 ones. So their weights are same, but you can see in how many bit position they are different. They are different in this position from most significant bit. This is the third one, then fourth one, then the fifth one, and this one. So there is a distance of 4. In 4 bits position, these two code words are different, and that is what is called Hamming distance. But this distance is not constant. If I see two other code words, this code word here and this code word here, and same way you see in how many bit position these two code words are different, you will see the distance between these two code words only 3. And 3 is the minimum distance between code words. Like that you can check the distance between all pair of code words. And the minimum Hamming distance tells what is the capability of these code words. That means how many error it can detect and how many error it can correct. So this minimum Hamming distance is very important. The next slide is also telling what I just said in the previous slide. What is the weight of a code word? That is the number of ones in code word I. And distance between code word I and J is the number of bit position in which I and J are different. So if I is this code word, J is this code word, their weight is 4 and 3 respectively, and their distance is 3. And Hamming distance is the minimum distance. Maybe there is more distance between code words, but we will go with the minimum distance between any pair of code word, and that determines the capability of that set of code words. How many errors it can detect and how many errors it can correct. And that is given by a formula which is given here. 2t plus s plus 1 has to be less than equal to d minimum. D minimum is the Hamming distance, and t is the number of errors it can correct, and s is the extra error that can be detected, and this one is a constant. Now if we put numbers in there, then we can see if s equal to 1 and t equal to 0, then d minimum required is only 2. With minimum Hamming distance of 2, only single error detection is possible, no correction is possible. But if d minimum equal to 3, we can make t to 1 and s 0, and then we can have single error correction or SEC. So this formula is very important, that tells how many error can be detected and how many errors can be corrected, and this d minimum is called the Hamming distance, which is the minimum distance between the code words. And if the Hamming distance is 4, then one error correction is possible, or double error detection is possible. One SEC plus, see, we'll put t equal to 1. So here we are getting 1 and here we are getting another 1. So correction means detection first, then correction. There is one detection and here is another detection. So 2 error detection plus 1 error correction is possible if d minimum is 4. Importance of the Hamming distance can be understood better if the problem is depicted pictorially. Like here, you can see that these circles are representing code words, valid code words, and when some error is taking place, it is changing that code word. Suppose it is here. Now, if that error word is equal distance from two code words, then you don't know in which way is the correct one, right? Correct code. So there only detection is possible, correction is not possible. With the d minimum 2, because from here you are going to error word and from error word you can get to here. So d minimum is 2 between the two valid code words. So if the error is here, which is equal distance from two code words, it's not possible to correct the error, because it can be this code word may have changed or this one, but you can detect that there is an error. And if the d minimum is 3, suppose this left hand side code word, one bit got flipped and the error word is this one, then assuming that there is a single bit error has happened, it will come back to this valid code word and not to that one. Okay, so that's why it is called single error correction. And in any place the code word is, it can be detected, so it is called double error detection or single error correction. And if d minimum is 4, then if the code word is here, error word is here, correct one will be here. It is a single error correction, right? But if the error word is here, then it cannot be corrected because it is equal distance from two valid code word, and you can reach here only when two bits are flipped, right? 1 bit flips, it will go there, 2 bits flip, it will go there. But if that is the case, correction is not possible, but it can detect the error. And then likewise for the minimum 5, it is double error correction is possible. If one error happens, this code word is closer, so it will, this is the right one. If 2 bits error happens, still this one is the closer, so this is the right code word. And single error correction and triple error detection is possible like this. Now let's see the 7.4 Hamming code, which is a single error correction code or ACC, and it is depicted pictorially again. And 7.4 means length of the code is 7 and 4 is the length of data. So 3 redundant bits are used, and here 4 data bits are already shown, and it is a Venn diagram, and 4 data bits are placed here, and in every circle you will be placing a parity bit, and you can see 3 parity bits will be placed, and each parity bit is covering a subset of the information bits. So here in this circle, if you put a parity, it will be covering this data bit, this data bit, this. 3 data bits out of 4, 3 data bits will be covered by parity 1. Similarly for parity 2, these 3 data bits will be covered. If I call the data bits D1, D2, D3 and D4, then here it is written P1 is covering D1, D2 and D4, and this is a parity checking. Even parity, if we say, it will count the number of ones already there in the data, and to make it even, it will put a 1 here, and if these 3 already even, then the parity will be 0. So let's see here, the sender is doing all this encoding, right? Sender knows this is the 4 data bits, and suppose this parity needs to be calculated. 3 ones are here, which is odd number, so the parity bit value P1 will be 1 here. And for parity 2, because the 2 ones are here, to make it even, it will be 0. And for this also, 2 ones are here, and this parity will be 0. And it is telling which parity is covering which data bit. Out of 4, 3 are covered. So multiple check bits are employed in 7.4 Hamming code. 3 check bits. Each check bit covers a subset of the information bit, and subset overlaps so that each information bit is at least into subset. So after putting the parity bit, sender is sending it, right? Or maybe this data is saved in the memory as a code word, and something happens and data is getting flipped. It was 1 before and this is 0. So if it is sent through the noisy transmission line and this bit got flipped and it became 0, now the receiver will calculate the parity again. So when it is checking the parity, and he knows that it is a even parity system, if it is 0, 1, 1, then it shouldn't be this parity that he has received, should be 0 and not 1. Okay, so he knows there is some problem in this circle. But in this circle, 3 data bits are there, he has to pinpoint. First of all, he detected it, now he has to pinpoint which 3 is problem. Now this parity will also be also getting recalculated, and here there is a 0. If this parity 0, 1, 0, then there should be an 1, right? So it is the problem between this parity bit and this parity bit, and this parity is okay. These 2 ones are there, parity is 0, it is okay. So problem is in red circle and blue circle, and red and blue common is only this bit. Other bits are, this bit is also common, but this bit is for the green circle also. Only the bit that is common in these 2 circles. That means the parity that is covering this bit, that is the problem bit, and that will be flipped. That 0 will be flipped to 1, and to make all the parities even parity. And this is the way 7.4 Hamming code can do single error correction. So To achieve the same thing more systematically, the data bits are represented as vector of length 4 because our data word is 4 bits long. So data bit 1 is 1 in one position and other are 0. Similarly for D2 it is set to 1 and in other position set to 0. So these are the 4 data bits, D1, D2, D3, D4. Similarly for parity bits, depending on which data bits they are covering, they are set. Like parity 1 is covering D1, D2, and D4. Parity 2 is covering D1, D3, D4. Parity 3 is covering D2, D3, D4. And when you write parity bits and data bits all together, it will be a 4 by 7 matrix and it is called a code generator matrix. I have depicted the parity columns blue and data columns with black color, and the data columns are a identity matrix. They are say in the diagonal position it is 1, and then the actual data to generate the code, suppose the data is 1011, so this 1011 will be multiplied with this code generator matrix and it will generate the code, 7 bits long code, and out of that this 3 bit is redundant bits or parity bits, and last 4 is the data bit. See the last 4, the data here 1011. So 1011 and 010 is they are 3 parity bits. That is the way it is mathematically computed. There is another way to compute. I will show that also to you. Now let's see what the receiver will do after receiving the code word. It will check whether the code word received is right or wrong. It will look for error, and if error is found, it will correct it. So if the receiver received this code word 0101010, in the previous when the code was getting computed by the sender, it was 1011 here, right? So one bit has flipped and it became 1010. So receiver knows first 3 bits parity and last 4 bits data. So it can also calculate the code word taking that data 1010 with the code generator matrix. It is getting a code, and here it is getting a parity bits which is different, 101. It received 010 with the same data. It is generating different parity bits. So the receiver knows that there is some problem. So it takes out the received parity and recomputed parity, and if they are XORed, it is generating 111, and it is called syndrome word. If the syndrome word is not 0, that means error has happened. If the syndrome word is 000, no error has happened. Now after knowing the error has happened, this syndrome word 111, which is 7, right? So this says the 7th bit position has flipped. You know that everything we are numbering from here 1, 2, 3, 4, 5, 6, 7. So it knows that this bit position has flipped, and it will make the correction with 1011. Okay. Either it is done this way or there is a checker matrix is also there. It's a 3 by 7 checker matrix called H. First 3 column is for the parity bits identity matrix. Only one is there, diagonally ones are there. And then last 4 columns are for the data bits that each parity is covering. Like parity 1 is covering data 1, data 2, data 4, parity 2 covering data 1, 3 and 4. Parity bit 3 is covering data 2, data 3, data 4 bits. So this checker matrix will be multiplied by the received code, 3 by 7 matrix, 7 by 1 matrix, and it will get a vector 3 by 1 syndrome word vector. And if the syndrome words are not all zeros, error has happened. And this 111 is saying it is a 7th bit position where the error has happened. So it is corrected in this way. Now we are going to see a bigger problem. But before that, let's go through the error correction steps again. When data is saved in memory, M is the message bits, M number of message bit, and previously we were depicting with data bits, right? You can call it as message bit also. And K is the code bits. Codes have been determined by the generator in the encoder side, and it is saving M plus K bits here. And when data is getting retrieved from memory, message is getting retrieved and the parity bits are getting retrieved, then the parity bits are again recomputed, which is coming out to be K prime, and they are compared because now it is going to give the syndrome word. If both are same, syndrome will be all zeros, and if not, the syndrome word will tell how to correct it and data will go out. Okay, and if the parity bits have no data correction capability, then it will give a signal that error has happened. Now see if the data size is bigger. We gave example with 4 bits data, 3 bits parity is required. So there is another formula by which one can determine how many parity bits are required. And that is given by this formula. 2 to the power k minus 1 has to be greater than equal to m plus k. M is the message bits, k is the parity bits or redundant bits, and this k is here. 2 to the power k minus 1 has to be greater than equal to m plus k. So if my data bits is 8, then the check bits required should be 4, because 2 to the power 4 minus 1 is 15 and 15 is greater than 8 plus 4, 12. If you take 3, you cannot satisfy this equation. 2 to the power 3 is 8 minus 1, 7, and 7 is not greater than 8 plus 3. Okay, so like that way, if the data bits are bigger and bigger, number of check bits required is given here, calculated according to this formula. And also it depends on the aim of the correction is single error correction, and if the aim of the correction is SEC or double error detection, then the check bits are getting one more. Every time it is one more. And then the percentage overhead is also given. If data bits 4 bits, check bits 4, then 50% overhead. But as the data bit size is increasing, then the percentage overhead of the code word is decreasing. Now let's solve a bigger problem where the data bits 8 bits data, and we already have seen from that table that 4 redundant bits are required. So total code word length will be 12. So we can call it as a 12 by 8 having single error correction code. And this time, instead of those generator matrix and checker matrix, we are going to solve it in this tabular fashion, because we also have to know which code bit or the parity bit or the check bit is covering which data bit. So here we are creating a position table with the first row is position number of the bits, position 1 to position 12, because there will be code word length is 12. And these positions we have written once with the decimal number, and next row we have written the same thing as a binary number, because we need this binary position number. We are placing the check bit where the position where there is only one. So check bit 1 is in position 1 and check bit 2 is in position column number 2, and then check bit 3 is in column 4, because in third column there are 2 ones in the position number where we cannot place it. Similarly, for check bit 4, we are putting it in position number 8, because there is only 1 in this position number. And this time just keep a note that we are counting the position number from the right hand side, Previously we counted the positions from the left hand side, so it will be just a mirror image, but the way you are putting it, you keep a note of that. So the first column is check bit 1, column 2 check bit 2, column 3 check bit 4, check bit 3, and column 8 check bit 4. And in the rest of the position number, you place the data D1, D2, D3, D4, D5, D6, D7, D8. And now these positions are telling that this check bit 1 will cover which data bit. Check bit 1 has a 1 in the first one, no? So it will cover the data uh, in the position number where there is a 1 in this place. Here there is a 1, here there is a 1, here there is a 1. This one doesn't have a 1 in the first place. 2 to the power 0 is not there. So, and then next one is this one, and next one is this one. So C1 will be covering D1, D2, D4, D5, and D7. And it is a even parity checking. So it is going to check D1 XOR D2 XOR D4 XOR D5 XOR D7. Is it understood? Now let's see what check bit 2 will do. This is check bit 2, which has a 1 in the second position, and it will be covering the data which has a 1 in a second position. So it is covering D1, then D3, then D4, D6, and D7. Okay, so it is written C2 equal to D1 XOR D3 XOR D4 XOR D6 XOR D7. Now check for check bit 3. Check bit 3 is here, the arrow is put here. And it will be covering D2 because check bit 3 has a 1 here. And D2 also has a 1 here. Then D4 has a 1 here. Next should be D7 and D8. Okay. So check bit 3 is covering D3, D4, and D8. So D2, D3, D4, D8. D2, D3, D4, and D8. Okay. And the last one is C4. C4 is this check bit 4, and it is going to cover rest of the database because C4 has a 1 here, and this position also has a 1 here, 1 here, 1 here, and 1 here. And in this position, D5, D6, D7, and D8 is here. So C4 is D5 XOR D6 XOR D7 XOR D8. Okay, and this is the way the code words will be generated. After you know the check words, you can just put all the data bits together and all code bits or check bits together. You do not have to interleave them like this. So now we are going to generate the code word, 12-8 code word we are going to generate for data word 00111001. 8 bits long data word. You have created the table, you have put noted their position, and you put the check bit in their proper column. You have put the data bits in their position, and you already know which check bit is going to cover which subset of data bits. Okay, now you are going to generate the code word. So let's put the data. Data was 00111001. Same thing you put it here also. So C1 will be this. You will be XORing this 1, 2, 3, 4, 5 bits, and you have to make it a even parity. So check bit 1 will be 1. Similarly for check bit 2, there are 3 ones. So check bit 2 is also 1. Check bit 3, there is only 1. So here also it is 1. and check bit 4, there are two ones, so here the check bit is 0. So the code word will be, now you are just putting all code words together, first 8 bits for data bits and the last 4 bits for code bits. So code bits are 0, 1, 1, 1. This one is C4, C3, C2, C1. And the data is D1, D2, D3, D4, D5, D6, D7, D8. Okay, so you remember the code word, and suppose the data gets corrupted. Now we are going to see how the receiver will correct it. So now it is saying, suppose the code word has changed from this one to this one. Where is the change? This position. D3 position has changed. Okay, D3 was 0 before, and now D3 has become 1. 1 bit error we are going for. So we already know the table where to put the data, where to put the check bits, and which check bit covers what. So at this time, the receiver will recompute the check bits. It already knows these 8 data bits, and it is recomputing the code word again. So C1 came out to be 1, C2 came out to be 0. So it is not matching. C3 came out to be 0 and C4 came out to be 0. So it is not matching, right? Here it received 0, 1, 1, 1, and here it generated 0, 0, 0, 1. So now it is going to uh, calculate the syndrome word. It will just XOR the recomputed code with the received code, and that will give the syndrome word, and the syndrome word is coming out to be 6. So it knows that 6th position the error happened, and in the 6th position D3 is there. So it has correctly identified that this bit has flipped, and it will put it back to 0. This is the way it is done. So error occurred in 6th position where D3 is there, and it is now corrected. Okay, learners, previously I created 2 other videos about error detection, and I also created computer codes like ASCII, Unicode, BCD, Huffman encoding lecture video. If you want to go through them, the links are given here. And thank you for watching this lecture video. I'll meet you in my next lecture video again. Thank you.